Hello, everyone. Let's talk about buffers and titration. So this is an extension or application of acid-base chemistry. And here's two really important concepts, things that actually affect us in everyday life. Okay, let's deal with buffers first. Okay, buffers are simply solutions that resist changes to pH. And what that means is, hey, you got this buffer solution and it's something special. You don't want people messing around with it or organisms or, nature. And so you put in a buffer to try and maintain the pH. And then like if stuff, contaminants fall into it, or if it's a cell culture and you're growing up something in it and the waste products or whatever you're growing in there changes attempts to change the pH, well, the buffer is going to work to cancel out those changes of pH and attempt to maintain the pH that it was set at. And it turns out that's essential for life. So there's medical conditions called acidosis and alkalinosis, I believe is the other one, where if the blood pH becomes too high or too low, it's life-threatening. And so in our bodies, we actually have buffers as well. Try and maintain our pH and maintain life. Okay, so what is a buffer? A buffer is supposed to resist changes to pH. So essentially there's two ways you can change the pH. You can add an acid or you can add a base. So buffer needs to deal with those two things. So what do? Well, if the contaminant is an acid, then the buffer needs to hit it with a base. If the contaminant is a base, then the buffer has to attack with an acid, right? Acids and base neutralize each other. The trick though is that you need both an acid and a base. So you can't use a strong acid and a strong base because they will react with each other. So a buffer is where you use both a weak acid and a weak base. But that's not all. To make an effective buffer, you want to pick an acid, a weak acid, and then use its conjugate base so that these two are connected, they're related. Or you can say, hey, I got this really cool weak base I want to use, so let's use its conjugate acid. Okay, so in a previous video, we defined conjugate acids and conjugate base, and we'll review it here too. Here's some examples of some buffers. You might recognize the acetate molecule here, the polyatomic ion, and with an H in front, makes it an acid. And then is this one of the strong acids we have to memorize? No, therefore it's a weak acid. And then when this molecule donates its H+, you're left with acetate. That is the conjugate base of this acid. And then the salt of the conjugate base is, well, we can put any spectator ion in front, right? So when H+ is released, you get the acetate ion. This is weak, so actually, sometimes H+ is captured by acetate. Acetate accepts it as a base and reforms acetic acid. So here's our weak acid, and here's the conjugate base. What became of the acid? It turned to acetate, so that's the conjugate molecule. And then what's its property? Is it acidic or is it basic? It's the opposite of what you started with. So you started with a weak acid, so the other component, the acetate now, is going to be a conjugate base. But you can't just have a bottle of acetate ions. They're all negative, they all repel each other. They would escape out of the beaker as they repel each other. So to make a stable compound, you need some spectator ion, cation, to neutralize the charge and create a salt. Salt is just, from the chemistry point of view, it's just simply some combination of cations and anions that makes a neutral compound. So sodium or potassium, calcium, there's lots of choices you could use as the salt form of the conjugate base. But if you start with acetic acid, then you have to make a salt using acetate. And the counterion can be anything else. Suppose you want to go after the combination of weak base. Well, ammonia is a weak base. So when ammonia grabs H+, it turns into the ammonium ion. And then to make a salt, we need to add a conjugate anion. Sorry, we need to add a counter ion. We need to just bring in a spectre ion, so maybe chloride. Or you could use, I don't know, well, bromide. What are some other anions? You gotta be a little careful that you don't form insoluble compounds or bring in another weak acid or weak base. My mind's gone blank. What else is there? There's sulfate, but that's not gonna work. Phosphate, no. There's other reasons. If you take more chemistry, we can discuss the problems with sulfate and phosphate outside. Anyways, should have said that the buffer is composed of a weak base. Here's ammonia, weak base, and then the salt. Okay, so now I formed a salt of the conjugate acid. The conjugate acid is actually the ammonium ion, but make a salt out of it, a stable neutral compound. And then here we go. Our blood is actually buffered with bicarbonate ions. So there's, well, this is amphoteric. That's the letter A there, amphoteric. That means it's both an acid and a base. So that's very clever. That's a nice use of bicarbonate ions. In our bodies, there's an H in front that can be donated, making bicarbonate ions an acid. And then it's negatively charged, and there's a bunch of oxygens with lone pairs that could accept another H, and that could act as a base. In our bloodstream, sometimes bicarbonate is paired up with sodium. It can be paired up with some other soluble blood proteins, potassium, calcium, other things like that. So the buffer really is, it can be a lot of different salts. But it turns out you just need one of these, one bicarbonate, to serve as both an acid and base. Unlike the other buffers where you need two components, the weak acid and its conjugate base, or the weak base and its conjugate acid. Cool. All right, so how do they work? Well, you need that weak acid to react with any added base. So who's adding that? You know, it's just contaminants, waste products from the cell culture, whatever's happening in your buffer, whatever you got. Maybe a chemical reaction, there's a side product that has an acid or a base that's being produced, and you're trying to do this chemical reaction in a buffer to maintain the pH. Okay, so the buffer's weak acid is there to attack anything that's being added that's basic. The buffer's weak base is there to attack anything that's acidic that comes into the solution. Okay, so I got some pictures here to try and illustrate this. So this is supposed to be a simple drawing of a beaker of water. So yeah, just think a bunch of H2O molecules. So if you just have pure water here, pure water, the pH is 7. It's neutral. And if it gets contaminated with a little HCl, then there's a bunch of H plus ions. And the more H plus is, the lower the pH. It's acidic. Darn it. Okay, so water has some problems maintaining the pH. It was 7, now it's much more acidic. However, you can start with this water containing a buffer, and I just randomly chose the ammonia-ammonium ion buffer solution. Okay, so this is our buffer solution. It's trying to maintain the pH, and oops, someone spills in some HCl again. So I drew in the same quantity of HCls. And so for an instant, hey, the solution has H pluses. It looks like the pH is going to be lower than 7. It's going to be acidic. However, the buffer sends its base after the H plus. So, right, the buffer has a weak base and its conjugate acid. If I contaminate the system with H pluses, the weak base is going to attack it. Bases accept H plus. So the ammonium ion grabs H plus and turns into the ammonium ion. And down here, same thing. Ammonia grabs an H plus, gobbles it up, turns it into ammonium ion, and effectively we've canceled out the H pluses, so there shouldn't be any change to pH. So the pH is supposed to be the same as it was before. That's the idea. Well, let's look at the other approach. Before we do that, let's just draw right out the overall reaction. The overall reaction is right here. Here's our reactants. We got the contaminant, HCl, that's providing H+. The buffer has ammonia as the base, and then base do your thing, grab an H+, and the product is simply NH4. Cool. If you want to add physical states, you can. Everything's aqueous, all dissolved. Nice. Okay, let's see what happens if someone contaminates the buffer with a base. And then we got comparison here. Hey, if you have neutral water at pH 7 and you spill in a little sodium hydroxide, oops, now there's a bunch of hydroxide ions and the solution becomes basic, higher pH. Dump the same quantity of sodium hydroxide into the buffer, and then for an instant, there's a bunch of hydroxide ions in there. It looks like the pH is going to rise, be basic, higher than pH 7, but the buffer will send its acid after it. So here's the acid component of the buffer, and it's going to attack the base. Acid, what are you going to do? Donate H+. H+ will go to the hydroxide ion to turn it into water. And then the ammonium ion loses H+ because acids donate H+, and it turns into ammonia. Hey, and I forgot to mention that when ammonia reacts, it's a base, so when it does its base thing, it actually becomes the conjugate. And so now this is available in the buffer in case some base comes along. And then down here, base did come along, and the base was attacked by the acid, the ammonium ion, and then the product was ammonia. And hey, now there's ammonia still present in the buffer. It's ready to attack any incoming acid. Okay, so this time the overall reaction is the contaminated hydroxide ion, and then you would say, okay, I have two components of my base. One's an acid, what's a buffer? Which one's going to attack the base? The acid. Which one's the acid? Probably the one with more hydrogens, the one that's more willing to donate an H+. And that's true. These are aqueous. Okay, and then we have to predict the products. Hydroxide ion, you're a base, so accept an H+. And so the minus plus cancel out, and the hydrogen goes on the oxygen, and you make water, which is now liquid, not aqueous. And the ammonium ion, you're the acid, so you got to donate H+. So nitrogen, you had 4 hydrogens, you're left with 3. And one of the hydrogens took off, carrying off the H+. Now you're neutral. More importantly, as a check, if you have a buffer, the product should be the other component of the buffer, right? So you start with ammonium ion, that's one component. It reacted to create the other component. It's a nice way to check your buffer reactions. Cool. All right, let's ask the question. Hey, can you prepare a buffer from HCl and NaOH? At face value, you might say, yeah, if you dump in a contaminating base, if we add hydroxide ion, HCl should attack that. Or if we add H+, the sodium hydroxide will attack that. Ooh, but these are strong acids and bases. So if you mix them as you prepare your buffer, they attack each other. And then you're left with, well, the H+ gets donated, hydroxide accepts it, and then Na and Cl combine, and now you have a saltwater solution, and that is not a buffer. You don't have any weak acids and weak bases. So something good about being weak, because they're weak acids, weak bases, they generally don't react with each other. Now that actually is an incorrect statement. They do react with each other. They're in equilibrium, right? So NH3 is going to accept H+ from, let's say, water. And as it accepts H+, it forms the ammonium ion and hydroxide ion. And then hydroxide ion can react with this and go back and forth. It's an equilibrium. So you always have some ammonium and some ammonia molecules in your buffer. And it just goes back and forth. Cool. But if you have a strong acid, strong base, you don't have a double-headed arrow, you don't have reversible reactions, they're one-way reactions. So adding HCl to NaOH just produces water and salt and it's done. And the resulting products are neither acidic nor basic. No buffer. Okay, here's another sample problem. Write chemical equations that show how a buffer composed of this molecule and that molecule resists changes in pH when either H plus or OH minus ions are added to the buffer solution. Okay, a lot of fancy talk, trying to express these ideas right up here. That's all it's saying. So, hey, what do you got? I want a chemical reaction. Okay, reactants going to products. I got a buffer. Ooh, what's a buffer? It's got a weak acid and its conjugate base, or you start with a weak base and you've got its conjugate acid. What do we got? Oh, there's an H listed in front. This is a weak acid. And then the C2H3O2, hey, that shows up again. Here's the conjugate. If I started with H listed first, there's my acid. The other thing must be the base, the conjugate base. Cool, all right, so I got my two components of buffer. I know which one's which. This one's the acid, this one's the base. They're there to attack any incoming H pluses or hydroxide ions. Sometimes there'll be a H plus being added. Other times there'll be a hydroxide ion being added. So there'll be two equations if you're asked to write chemical equations for a buffer. Sometimes it's acid coming in, other times it's hydroxide ion contaminating the system. All right, so how do you cancel out an acid with a base? So grab this molecule. And they're all aqueous. For full credit, get their physical states in there. It's a balanced, ooh, it needs to be a balanced chemical equation. All right, so what happens? Well, this molecule separates into sodium ions and acetate ions. And then just swap the cations. H plus goes on to here to make the other component. There it is. It makes the other molecule. And then sodium is just off floating around in solution by itself. So I just exchanged the Na and the H. That's your product, and then balance it. The Na is still there just as a free-floating cation. Second equation, hydroxide ion. You're a base, so the buffer needs to send the acid to neutralize it. These are aqueous. Okay. You might be thinking, I'm going to switch the cations. Well, there's no cation over here. So switch the anions instead. When this molecule, it's got H listed first, when this molecule does its acid thing, it's going to release H plus and turn into acetate ion. So H plus, stop hanging out with this anion, go to the other anion. Hydroxide ion, you're a base, so accept H plus and turn into water, which is a liquid. And then the leftover fragment is your byproduct, acetate. And it should be the conjugate base. It is. I know, it's missing the sodium, but that's because we didn't say, hey, you had sodium hydroxide. So it's okay, full credit. We got a balanced chemical equation, and we explained how hydroxide ion has been removed. There's no hydroxide ions in the product side. And H plus is gone. I know it's hiding here as a weak acid, but effectively there's no H plus ions all by themselves. Cool. All right, now for the full picture. It turns out that as you contaminate your system with the low acid, low base, it does result in a change in pH. So if you're dealing with a biology sample and you got buffered cell culture, or you're talking about blood and it's buffered, yeah, you can't just say, oh, it'll be fine. It's like, no, we need some precise measurements. We need to be a little more accurate. So let's talk about that a little bit. Let's say you start with a buffer that you chose to have equal amounts. We don't have to have equal amounts, but we chose to create a buffer that had equal amounts of, well, in this case, it's a weak base and it's conjugate acid. I chose, let's add some sodium hydroxide, and the buffer sends its weak acid after it. So the weak acid attacks the ammonium ion, attacks hydroxide to produce water and ammonia, and it does it down here also. And then once we're all done, hey, no hydroxide ion. That should have stopped the pH from changing. Well, it does help stop the pH from changing drastically. But let's count up things. We got 1, 2, 3, 4, 5 ammonia molecules here. And we only have 1 ammonium ion. Whereas before we had 1, 2, 3 ammonias, and we also had 1, 2, 3. We had equal amounts of the weak acid and the weak base. And now we have more of the weak base. So more base means the solution will be slightly more basic. It has more of the weak base in it. And thankfully it's weak, so it's not producing a whole bunch of hydroxide ions like a strong base would, but still it is basic. So the pH does change a little bit. Okay, but by how much? That's when you need this equation. You don't have to memorize it. You just need to be able to use it. It is such a useful reaction, right? Because the biology department uses this all the time, medical labs all the time. If you need to prepare a cell culture, you need to grow up some bacteria in the cell or a petri dish or whatever you need to do with life, or you're looking at someone's blood and you need to know, hey, what's the pH? You can use the Henderson Hasselbalch equation. What that means is you're trying to find the actual pH, and you need to know more about your buffer. It's going to have a weak acid and a weak base in it. So find the acid component and go look up its equilibrium constant. So in a previous video, we talked about how if you have an acid, I'll pick the acetate ion, acetic acid, that's what this acid is, H plus with the acetate ion. It can produce an acid and the acetate ion, and it's a reversible reaction. So it goes back and forth. Because it's an equilibrium reaction, we can write an equilibrium constant or the equilibrium expression where we put products divided by reactants. Our products are H plus, the concentration H plus, times the concentration of acetate, all divided by the reactants, acetic acid. In a previous video, we talked about this. Okay, and then because we're interested on the H plus side, how much H plus is here, we call this the acid equilibrium constant. And larger Kas mean more acidic, it's a stronger acid. So the Ka equilibrium constant, acid equilibrium constant, measures how strong of an acid the acid component is of the buffer. So you need to know that. You need the Ka. But what's the pKa? Same idea as if you have the H plus concentration. What's the pH? That's equal to the negative log of the hydrogen ion concentration. So do the same thing with the pKa. It's the negative log of the Ka. They're just related. Just remember to change the sign after you type in the acid equilibrium constant and hit the log button on your calculator. Make sure you change the sign. That's the pKa. And then we saw above that the amounts of weak acid and weak base can change. So you need to find out what they are now. So it's always the acid component on top divided by the, did I say that right? No, I didn't. It's always the base component on top divided by the acid component. So up here in this example, we had 5 of the base. So I don't know, does that mean 5 molar up here? And there was 1 acid, so underneath would be a 1. Divide the 2 and take the log and add it to your pK, and that will actually calculate the actual pH of your buffer. Cool, so very useful equation. You don't have to memorize it, just be able to use it. So let's get some practice. I keep the Henderson Hasselbalch equation in view though, because you don't have to memorize it. Okay, suppose you have a 0.01 molar, nope, just says 0.01 moles. Okay, so we're putting in HCl, how much? 0.01 moles of it, and we're adding it to a 1 liter acetic acid acetate buffer. And I misspelled afterwards. Okay, afterwards, yeah, whatever. The H plus, so the weak acid component, the acetic acid component now has a concentration of 0.1 molar. And then the acetate component, the weak base part, has a 1.0 molar concentration. Oh, and by the way, the Ka for acetic acid is 1.8 times 10 to the minus 5. Please calculate the pH afterwards. Okay, at least I spelt it correctly there. Okay, well, this is the Henderson Hasselbalch equation. This is the equation for buffers, and that's what we're given. So that's how you would know, oh, I need this equation because we're talking about a buffer. And we also have the buffer concentrations. Okay, so let's just crank it out. pH is equal to the pKa, pK plus the log of the base part, A minus. So you see how this whole thing has a minus sign. So A, it just means anion, I guess. So every acid will have the H listed first, followed by some anion. That's going to be the chemical formula of an acid. And then when it donates H plus, you're left with the A part, the A minus part. So that's just a generic way of indicating the base and the acid. Anyways, that's what it is. Look at the equation, realize, oh yeah, my H plus is the acid, it's on the bottom. Here's my H plus, and it's 0.1. The base, the A minus, is 1.0. Cool. What's my pK? Well, the Ka is this. So on the exam, I'm going to give you the equation for the H plus, and I need you to know what that says. It says, hey, go grab the power of H, which is where you take the negative log of that thing, the H. And then using this equation, you can create the pKa equation. Change the H to Ka, change the H to Ka. That's all you have to do. Oh, and let's crank it out. Get your calculator out. You need the negative log of 1.8 times 10 to the minus 5. Did it earlier, maybe, somewhere. There it is. It's 4.74. So now my pH is equal to 4.74 plus the log of 1.0 divided by 0.1. Crank that out. This turns out to be 1. And so the actual pH is now 5.74. Is this solution acidic or basic? It's less than 7, less than pH 7, so it's acidic. Okay. So it is kind of lower than 7. It is somewhat acidic. Maybe it was a buffer that wasn't supposed to stay at pH 7. To give you some context, then I asked the second question, hey, what would be the pH if the buffer was absent? So if there's no buffer, then all we're going to do is add 0.01 moles of HCl to 1.0 liters of water, right? So if we didn't have the buffer present, we still have a 1 liter solution. Well, it'd just be pure water because no buffer would be in it. And we're still going to add the same amount of acid. Okay, so what happens? Well, HCl, as you should know, is a strong acid. So all the HCl molecules split in H pluses and Cl minuses. And for every 1 molecule of HCl, you produce 1 molecule of H plus. Well, we didn't have 1 mole, we had 0.01 moles of H plus. And we have a liter of water. So what's the equation for pH? It's right off the top of the screen. There it is. To find the pH, we need to take the negative log of the hydrogen ion concentration. What's concentration measured in? The brackets want molarity. Molarity is moles per liter. Oh, we got moles here. We got liters there. So the hydrogen ion concentration is 0.01 moles in a 1 liter solution. Moles per liter, that's molarity. So take the negative log of, well, divide this out. 0.01 divided by 1 is 0.01. And it turns out, put that in your calculator, change the sign, the pH is 2. Ooh, who's more acidic, 5.74 or 2? 2, and it's a lot more acidic. It's the same quantity of strong acid though. So look at this difference. That's pretty significant. A very strongly acidic solution could have been created upon dumping in this much HCl into a liter of water. pH 2 is pretty strongly acidic. But if you got the buffer around, it didn't dip down to pH 2. It just came down a little bit to 5.74. Nice. So the buffer did its job. It slowed down or resisted the change of the pH. Not perfectly, but it did a pretty good job. Okay, enough about the buffers. Last concept for this, which is kind of related, it's a technique called titration. Okay, scroll up there. Yeah, there we go. Okay, so titration, we got some fancy glassware here. So not all titrations are done this way, but in a chemistry lab, this is typically how we do it. An industrial lab would do it the same way. There are some medical labs that will do a titration this way. The titration, what's that all about? Well, it's a technique that's going to use a solution of known concentration to analyze a solution of unknown concentration. The trick is you need to know what is present, but you may not know how much of that is present. There's lots of different titrations, one of which is an acid-base titration. Another titration is oxidation reduction. There's some antibody titrations you can do. There's lots of different titrations. But the idea is you put something in this measuring device that you know, you have the known concentration, how many molecules per solution. And then here's your unknown down here in this flask. You know what the molecule is, you just don't know how much is present. So let me look at the sample question. What's the concentration of H2SO4? Okay, if we're asking about the acid, that means we don't know what it is. So in the sample problem, we're gonna put some sulfuric acid in this container. And then let's say we have, why is this HCl? Because I made a mistake. Sorry, it's not two acids, only one. Okay, so let's say this has a total volume of 10 milliliters of sulfuric acid. We want to know how many moles per liter, what the concentration is. We don't know what it is, you just know the identity, sulfuric acid. So in the burette, that's the name of that fancy measuring device up here, we're gonna put in lithium hydroxide. Is that an acid or a base or what is that? It's got hydroxide ions in it, so it's probably, and it is, a base. Sulfuric acid has an H listed first, it's an acid. It's also a strong acid, one of the 6 that we're supposed to memorize. Okay, and then for the lithium hydroxide, the base, we actually know its concentration. It's 0.2 molar. And we also find out that it takes 25 milliliters to titrate. All right, so let's look up here and see what's going on. So what's happening is you start down here with 10 milliliters of HCl, 10 milliliters of sulfuric acid, and it is okay to add more water to it. Water is not going to put in more acid, water is neutral. So sometimes it's nice to have a larger volume so you can just see what's happening. You have that sulfuric acid down here. We don't know how many moles of sulfuric acid, so we do a titration. Load up the burette, this device, and you can't see the top of it, but it looks like it's full, and you start draining it. You start dripping in the sodium hydroxide into the sulfuric acid solution, and then the base reacts with the acid. Also present is some molecule that can change color. That's called an indicator solution or an indicator compound. And this specific compound is called phenolphthalein. It's a molecule that has no color if the pH is neutral or acidic. But if the pH is basic, it becomes this purplish color. Okay, that's an indicator because it's going to tell you when the solution becomes basic. So to do a titration, you put your sulfuric acid in this flask, add the phenolphthalein, and it won't have any color. Because if it's acidic, the pH is less than 7. Phenolphthalein has no color if the pH is 7 or lower. You start dripping in lithium hydroxide. The hydroxide ion hit the solution and react with the acid. And then if you only put in a few drops, there'll still be acid left over. But at some point, if you keep adding more and more base, as you add that base, as it hits a solution, it'll gobble up all the acid that's right there at the point where that drop hits. And then for an instant, there's more base right here, hasn't mixed yet. There's more base from the burette. And so now we can see the phenolphthalein change color where that base is present. If you swirl this to mix, then the acid over here can mix with this and cancel it out, neutralize it. And afterwards then, after the sodium hydroxide gets reacted with, it's all gone, then you still have a little bit of acid left. So then you start adding this slowly, drop at a time. And at some point, when you add a drop and you swirl it, it'll stay colored. What does that mean? It means that you've reacted all the acid and now there's leftover base. Well, be careful not to have too much leftover base. You want to stop adding drops right when this maintains a steady color. I mean, actually, you want it to be lighter than this because it gets darker as you add more base. And wait, you want to know how much base did it take to exactly match the number of moles of acid in the solution, just so this starts to change color. Cool, because if you find out how much to add, and this example is 25 milliliters, you can then calculate how many moles of base that were added. And then from that, you can figure out how many moles of acid must have been there to neutralize completely with all the base that was added. So that's the trick. You add a precise amount of one reagent to another. You do it slowly near the end point, right where the moles are starting to match up. And you have to have some indicator to tell you when to stop. And that, in this case, is a phenolphthalein changing color. Cool. Okay, in lab, we'd ask you to do a titration and actually do some calculations in your lab report to figure all this out. On exam, you're not gonna have to run down the lab and do the experiment. You'll just get the data and you'll have to do the calculations on the exam. So let's end this video with a sample calculation. Okay, so this is the phrasing that I'll keep on the exam if I ask about titration. And using the word titration in the question, that'll be a good clue. All right, so the question reads, what is the concentration of H2SO4 if 25 milliliters of 0.2 molar lithium hydroxide is required to titrate 10 milliliters of the sulfuric acid solution? Try using dimensional analysis to help you answer this question. Okay, so what do we want? We want concentration of H2SO4. So what's the unit for concentration here? Well, the unit for concentration of the base is molar. So let's keep it the same. We want the molar concentration of H2SO4. Let's break that down for some added help. Molarity is equal to moles of H2SO4 divided by liters of solution. So we need to actually get these two numbers. Let's calculate how many moles of HCl that reacts with this base, excuse me. And let's also find out how many liters of the solution, H2SO4 solution, that we started with. So how many liters of H2SO4 do we start with? Here it is, 10 milliliters of HCl. So we had 10 milliliters of H2SO4 solution, but I need it in liters. So a quick little dimensional analysis to change it to liters. I need a number, a conversion factor that changes milliliters into liters, and it's not given to you on the exam. I need you to memorize that. It's 1 liter for every 1,000 milliliters. Cool. That'll cancel out your milliliters. 10 divided by 1,000 is 0.01 liters. Okay, so now we know the denominator of our answer. The molarity is going to be some moles divided by 0.01 liters. Now what do we want? Well, now I'm going to go after the moles of H2SO4. That's what I want. I'm going to use dimensional analysis to help me find out what that is. Okay, this is what I want. So what am I given? Reread the question, find out what are some digits. Well, here's 10, but I already used that. Here's 25, and here's 0.2. So the guideline is to start with a single unit number. And I know that looks like a single unit, but molarity is actually 2 units hiding in there. 0.2 has 2 units. It's moles per liter. So you want to start with this single unit number. Start with 25 milliliters. And what molecule is that describing? It's 25 milliliters of a 0.2 molar lithium hydroxide solution. Okay, found out what to start with, what I'm given, 25 milliliters of lithium hydroxide. What do I want? Moles of sulfuric acid. Next, find conversion factors that change the milliliters into moles and the lithium hydroxide into sulfuric. How do you change a molecule into another molecule in dimensional analysis? With the balance equation. Yes. So this is a loaded question. There's several steps here. At the heart of titration is a chemical reaction. The acid is reacting with the base. We're going to need to get the balance equation for that. So why don't we just do it now? So we know that we have an acid and reacting it with this base. The question is not asking us to report or give the balanced chemical equation. So if you don't want to put in physical states, you don't have to. And I'm not going to. Save a few seconds. Okay. Those are my reactants. How do I predict the products? Try switching the cations. Okay. So what are the cations here? Well, the hydrogens are listed first. They come off as H+. And then you're left with sulfate. You either remember from the polyatomic ions that SO4 is 2-, or you just figure it out. Hey, there's 2 H+. The whole thing's neutral. That means sulfate must be a -2. Over here, where's my cation? Well, we got the polyatomic ion hydroxide and lithium straight off the periodic table. Likes to become a +1 cation. It's in column 1. 1 valence electron, likes to kick that out and become a +1 cation. All right, so let's switch them. And I know there's 2 H+, only 1 lithium, but that's balancing. Let's not worry about balancing this yet. Let's just predict the products. So switch them so that now lithium hangs out with sulfate and hydroxide is going to hang out with the H+. We switched the cations. It was lithium and hydroxide, hydrogen ion with sulfate, switch the cations. Lithium, you're with sulfate now. Hydrogen, you're with hydrogens with hydroxide ion. Okay, then pair these up to balance the charge to create a stable molecule. Well, sulfate's got a -2. Lithium only has a +1. I'm going to need 2 lithiums to make a stable molecule. Lithium sulfate. For this reaction, hey, plus and minus cancel out. You recognize this as water. There you go. And we correctly predicted the products. Next, now let's balance. I like to save the simplest molecule for last. The simplest looking to me is water. There's only 2 elements present. Everybody else has three elements present. So I'm not going to balance the H's or the O's till later, till the end. So let's go after the sulfur or the lithium. Maybe sulfur. Oh yeah, there's 1 S on this side, 1 S on that side. It's balanced. Lithium, there's 2 here, but only 1 there. So let's put a 2 here. And now it's time for H's and O's. I guess we'll just do H's first. Got 2 H's here and 2 more there for a total of 4 H's on the left. Ooh, but I only have 2 H's on the right side. So let's put a 2 here, so we have 4. And the hydrogens are balanced. Oxygen, there's 4 O's here, another 2 here for a total of 6 oxygens on the left. On the right side, 4 O's and 2 O's. Yay, it's balanced. Everything's balanced, we're done. Nice. And so when it's time for us in dimensional analysis to change lithium hydroxide into sulfuric acid, the conversion factor is 1 mole, right? The units for the chemical equation is in moles. 1 mole of sulfuric acid reacts with 2 moles of lithium hydroxide. It's a 2-to-1 ratio. Wait, the units are in moles? Yeah, that means we have to get the lithium into moles. So we can use that conversion factor. So let's get out of milliliters and then change the moles. Well, what do we know about lithium hydroxide? It's 0.2 molar, which is the same as 0.2 moles, per liter. I got milliliters. We can change that to liters. We just did it over here. On the right side, 1 liter is equivalent to 1,000 milliliters. And now cancel out the liters. And then let's use concentration, the molarity, to cancel out the liters. The solution has 0.2 moles of lithium hydroxide in 1 liter of solution. 1 liter of solution contains 0.2 moles of lithium hydroxide. The liters of solution cancel out. Left with moles of lithium hydroxide. Now it's time for the balance equation. Well, the recipe, the balance equation says you need 2 moles of lithium hydroxide to react with 1 mole of sulfuric acid. And now the moles of lithium hydroxide cancel out, leaving us with the units and the molecule that we want. Awesome. Okay, so 25 times 1 times 0.2 times 1 gives you a number. And you divide it by 1,000 times 1 times 2. So multiply across the bottom, across the top, and divide those 2 numbers, and you should get, I got 0.0025 moles of sulfuric acid. This is really messy. Let's rewrite it down here. What do we want? We want molarity of H2SO4. And the molarity of H2SO4 is the number of moles of H2SO4 divided by the liters of H2SO4 solution. Well, the liters is 0.01, and the moles, we just calculated it, it's 0.0025. Divide this out, and the answer is 0.25 molar H2SO4. There we go, yay. That's the concentration of sulfuric acid. Very nice. Okay. Let's take a break. Maybe rewind that when it's time to do some homework problems so you can get used to the method. And then I'll see you in the next video.